Okay, so this is in the week four D2L pages, ARM history and perspective. It has a whole bunch of links. I want to continue on with what we were talking about a little bit last day. We also have, on to the links. So from Wikipedia, again, talked about last time. Um, ARM, they kind of say ARM doesn't really stand for anything anymore, but it did stand for Advanced Risk Machines. Again, what is RISC? And as the instruction sets have grown and as the architectures have grown, it's kind of like, okay, it's ARM. But Advanced Risk Machines, and originally it was Acorn, and uh, they developed the computer for the BBC Micro in Britain. A lot of the world was running 6502s at the time. This is kind of like the early 80s, 82, 3, 4, 5 kind of thing. During that time, Commodore 64 was and up till very recently had been the largest selling kind of home computer at the time. The outsold IBMs, all of that during that kind of reign. Over their time, they sold about 15 million units, and then Commodore came up with after the Commodore Amiga, for instance. The Amiga was way before its time as far as graphics. You were able to play some arcade style graphics at that time, and if you went for an IBM machine, it was a green screen or amber monitor, or if you're really lucky, paperwhite, but kind of text only. Uh, and then there was something called CGA, which gave you really rudimentary graphics. And again, at that time, over on an Amiga, you could play games that were very arcade-like. And so that was Commodore. And they did some missteps and kind of uh, aren't around anymore. There's still groups on the internet that love the old Commodore 64 games or the Amigas. There's still an Amiga magazine, I think, being published, and various um, groups around that. Um, but around those times in Britain, we had the BBC computer and Acorn. And again, um, if you go and look, the ARM one was really designed on an FPGA for kind of proof of concept. ARM 2 was actually physically made. And then they came up with this Advanced Risk Machines licensing, and it was a different kind of model where you didn't actually have to make stuff. You just had to license your intellectual property. And the original ARM kind of spun off of that licensing model, and then they have different families, and you can see there's the ARM Cortex series, which was really keyed toward the stuff that we do. So low power, kind of high performance, has a bunch of peripherals in it for the embedded market. Then there's the ARM A kind of series, and that's you have more RAM in it, maybe better graphical uses used in phones and that kind of stuff. So they have all sorts of different ones. And the neat thing is, a manufacturer would just say, hey, I want this kind of thing, and they can license parts of the different technologies that they want, and then add their own things to it. And so it talks about different cores. Now, one of the things, I'll see if it's down here. Um, the ARM one again was done by the VLSI, and actually Apple was right in there. Apple was an early investor. That should look kind of familiar. That's like similar to the picture that we have for our Cortex M, in that there's an ARM processor. That whole big square is a piece of silicon, and then there's a an actual ARM core, which has all our registers and things, as just a little piece of it. And then it has the interface to a bunch of other things. We have the advanced high-speed bus, which goes over to your RAM and your flash. And again, we talked about that being, there's a separate area for your code and your data. That was that Harvard architecture. But one of the things that confuses everything is that we then put it in one 4 gig linear address space in a memory map. So when we use it, we just think of it as all being together. Well, that's if it was actually together, like in Motorola, where your code and your data are in the same space. You kind of think of it like that, even though they're actually in separate places, but they've mapped them into the same addressing area. So we have this advanced high-speed bus for our static RAM and our flash and maybe our networking and all of that. And then you have the advanced peripheral bus here, which has your UARTs and SPI actually off of that. They say the Ethernet MAC. That's one thing actually on your devices. There is a physical, there is the module for doing Ethernet. It just lacks the physical module. So you can buy a little physical interface chip and the connector, and you can plug Ethernet into it. And some of the boards that you can get actually have done that for you. Yours doesn't have that. It has the pins for it, and you can actually hook a unit up, and it has the silicone inside to be able to give you that whole Ethernet. We also have USB, and again, the silicone's on there to be able to handle USB. It has one connector on there, and it has the ability to have another USB, and it doesn't have the physical interface over on that. But that's all coming from way early on. You can see the similarities between what we have in our map and what this was. Okay, and then it says, hey, you could have ADC 0 to 7 down on the left-hand side. It has timers. It started off with 0 to 2, so we had our 3 timers. We have a ton of timers. We have a ton of serial interfaces. We have a ton of UARTs in our device, so it's gone from there. Now, one of the things it says here is in 2005, about 98% of all mobile phones sold use at least one ARM processor. And most of the ARM processors now have gone, especially in phones and things, where you'll have multiple cores. And so, in fact, you could even get ones that have maybe 4 cores, and they might even start to have lower powered cores in amongst higher power cores. So they're going, okay, you want most of the time, if you're waiting for a phone call or whatever and it's in your pocket, then go into a low kind of power mode. So put the processing on the lower power cores and put the high power cores to sleep. And then when you want to play a game or do something that requires more, it fires up the higher power cores. So they're trying to do things to extend your battery life. In 2010, it said 10 billion were produced. And again, we have just so surpassed all of that. Around 7 or 8 billion were just in a quarter alone. We're about 200 billion right now. So in the next 10 years, they've more than 10 times increased. So they're just in absolutely everything. And again, it's selling just the IP cores. And so, it's kind of a nice business. You just have the intellectual property, and then you don't have to worry about anything. Lots of different architectures. I'll just point this out just a little bit. And so the naming is really awful. If you look at, there's an architecture and it's ARM v something. That's the architecture, and you can go and look and see. And then in that, there's different families of the chips. So in the V4 architecture, there's the ARM7 TDMIs. That was the Nintendo Game Boys and that kind of thing. And then you say, okay, an ARM architecture 6 is actually known as an ARM 11. I hate, and I don't expect you to remember any of it, okay? So when we go down here, I'm looking for an ARM Cortex M4. That's what you have. And you'll see ST names them STM32F4. Well, that's an M4. F signifies the floating point. Well, I don't even know if that's anywhere there's an M, there's an F. Okay, and so that's what you have. Um, then you look at um, the R. Anytime you see an R, they're talking about it's supposed to have some real-time aspects of it. So to be able to have a deterministic response to things. Um, Anytime you see an A, they've put things in more for less for kind of microcontroller use, more for like phones and those kind of things, have more memory, more graphics end of things. So all sorts of different architectures. So it spun off from the original kind of licensed IP into all sorts of different families. Because somebody said, I really like this, but I need this kind of thing, or I need it to have cache, or I needed to have some sort of pipelining, or this kind of thing. And so you have all of these different ones in it. Um, And then some of the latest ones that you're going to see are now 64-bit. It's been 32-bit for a long time. When we look at next term, the Raspberry Pis, the Pi 4s are 64-bit. Okay, and so it's still an ARM architecture, but now it's gone from the ARM 7 architecture to the ARM 8 architecture. And where that's important to know is they just have kernels and they're based, they say, a 7 kernel or an 8 kernel. Well, one's 32-bit, one's 64-bit, because that's the architecture. Okay, and that's all they tell you. They don't show it to you any kind of other way than you say, oh, I have this other one. Okay, so real confusing in the, an ARM Cortex A55 is the version 8.2A architecture. So we'll look down there. Now, one of the things, if you actually look in the registers, it shows over here, so R0, R1, R2, R7, all the way down to R12. Then there's some different ones going down to R15. A number of books that are out there showing textbooks for teaching ARM do all sorts of examples in assembly language. Now, you did assembly language in PIC, and PIC we had a W register to be able to put data in. This gives you a bunch more. It's kind of more like a Motorola. Motorola had registers D0 to D7, A0 to A7 to be able to do things with. So it gives you more flexibility. I wouldn't, well, when you go and program assembly, it's awesome, and just one line of code does one thing, but you have to put a whole bunch of lines of code to be able to do things. In fact, years ago, that LCD display that you had, the 2x16 LCD, had to all be written in assembly language, which takes a bunch. And so one of the nice things about ARM, they have a whole bunch of registers, which an assembler can use and give you pretty optimized code. It, I don't think, makes a lot of sense for you to be coding it in assembly language. You do get to know the registers better, but really, who cares? You want to have an application do something for you. So it's learning the development tools, having some appreciation for the different buses and what you would have to turn on. And again, you have a better time with it because the graphical environment does everything for you. Whereas if you are in some other environments, and even not that long ago, you had to set all that stuff up yourself. So it's nice that this does it for you, but then you kind of go, oh, I don't need to worry about it. So that's why we went through the GPIO and looked at the registers, because it's still there. And sometimes you do things and it should be working and it's not, and you can go in and see what the actual registers were set up as. I remember a few years ago with the PIC, we were using the PIC that's in those little Simon Says boards. I got that unit, and I set it all up and set the registers up to be able to go and sense the buttons, and things weren't working right. And then I went in and looked at the code that the library generated, and it wasn't setting the right bits. They fixed it in another release, but the chip was new and somebody screwed up. They probably copied something over and things weren't exactly right. And so there was a bug. It was their fault, not mine, but I was able to go in and look at things. And generally, if something doesn't work, it's your fault, okay? But sometimes it's not, okay? And so being able to look at that. When we go to in a few labs, we're going to look at a TFT display that you have, and we're going to use a library from Sager called MWin, and in fact, the licensed ST version is called STEMWin, ST's MWin, and one of the so it's really nice in that if you went to go and get a license yourself, it would cost you 10 to maybe 12 grand, depending on all the different modules. It's there. It's already downloaded when you downloaded the support for your board. One of the drawbacks of it is because I didn't pay the 12 grand, I don't get access to the source code. So when I step through my code, if it jumps off to the graphics, it just says, I don't know what you're talking about. I can't see the code because it goes into a compiled library. Okay, so if something's going wrong, you can't tell what's going wrong or where it got stuck in the library. Okay, that's the advantage you get of paying the big money. But on the other side, I get to use that whole thing, and it's probably my code, not the library, that's messed up, and you can use it even in a commercial application. Anyway, so we have access to the registers. One of the nice things about ARM was they designed it to make it to be able to use C code and C code quite efficiently. Years ago, on a little step, I was programming in Intel 8051 architecture, and I wrote some code for a little underwater submersible for a company, and it was about 2,000 bytes of code, and it was about 50 pages or so of code to be able to control this little underwater submersible. It had a 3-wire tether, and it had a camera and all of this kind of thing. And it was all in assembly language, 8051 assembly language. And a C compiler came out for the 8051, and it wasn't too much money. It was about $100, and I sent away for it. And I went, okay, this C compiler, and we'll see how it works out. And so I coded all my subroutines and things from assembly into C functions, and then I took my 50 pages to probably 10 pages or so of just C function. So it made it easier for me to go through and see what was going on with it. When I compiled it, though, it went from 2K, 2,000 bytes of assembly language code to 8,000 bytes. So I was a way better assembly language programmer than that C compiler was. Nowadays, you would be hard pressed to beat a C compiler. The GCC compiler on the ARM, they have the silicone is designed to take advantage of the fact of that C, the space that C needs to be able to do things. They've optimized it for C compilers. The ARM is very optimized to be able to do that. You will look at a compiler, and currently I'll show you what some of the different options are, but I can say, you know what, the most important thing to me for a compiler is speed. So you can optimize it for speed. Or I can say, really, I want to optimize it for debugging. We're kind of in the debugging mode right now. So it's not the fastest code you're getting, but it puts in things to let us step through our code. I can also say, well, really what's most important is size. I can give away some speed, but I really need to fit it into something a little tighter. You can choose what you want with the compiler, and it will try and target that. Okay. So years ago, it was just, here's your source code, here's your assembly, that's all you get. Okay, so you'd be really hard pressed. Now, if you're a good assembly language programmer, you could go in and optimize some of the code probably better if you were good, okay, at doing that, really knowledgeable about the inner workings of one. But one of the things that they have done, we are using the HAL, the hardware abstraction layer. Well, the hardware abstraction layer is on top of this CMSys, which is another abstraction layer. There is also, let's say I was running some code and found that whatever I was doing, maybe I was doing some calculations for something and it was taking too long. There are other drivers, and the HAL API talks about other drivers called low-level drivers, which aren't portable across the family of chips, but are more optimized, have less layers to go through, so are more efficient. So even in C, I can load in other drivers. And one of the other things that we can do with our IDE is I can do something called profiling. And so I can run my code and then get a picture of where my code spends most of its time. So there's no point in me optimizing the keypad routine if 90% of the time it spends it in the TFT routine, because I'm trying to optimize something that it spends 10% of its time in instead of where it spends 90% of its time in. So a profiler will let you do that. And we have the ability with the tools that ST has given us in the CubeID to do that kind of thing. Okay. All right. Let's wanted to show you. So again, there's some of our assembly language. If greater than A equals A minus B. So that's kind of that instruction. And again, we could go through all of that. You've done it a little bit for pick, saying there's where it is. If you had to roll up your sleeves and you were hired to write low-level routines, you would have to figure out what all this does. It does. Otherwise, we're not going to do that. On the links as well, I have a brief history of ARM, so it goes through kind of some of the stuff that I've talked about here, and just going through the beginning. And there is a little link to something called Micromen, which was all about the BBC microcomputer and when it was first going. There's their barn where they first, everybody always starts in a barn or a garage. You know, Google had a whole rack in one of their first employees' garages. They rented out for a while. So everybody starts there. One of the things about the ARM7, and I mentioned the ARM7 was in the Nintendo Game Boys and things, especially when it came to the phone market, like with Nokia, when the ARM7 was around, what they found was there was a limited amount of memory, and when you had a 32-bit architecture, if I'm just doing something simple, some simple instruction like add one, if your instruction is 32 bits, I've wasted some code space to just add one. We do that all the time. And so the ARM7 gave you the ability of going into this, what's called a thumb instruction mode, which was 16-bit. And you had to manually switch it from 32-bit to 16-bit to say, now I could use two 16-bit instructions, and it took the place of one 32-bit instruction. So you could go into this 16-bit mode, save some space, go to 32-bit mode when you needed 32-bit instructions, and you had to know what you were doing and switch back and forth. When we went, it was a hit because you could save a lot of your flash instruction space. When we went to the Cortex series, it has that integrated in, but it does it. You don't have to worry about it, even think about it, even really know it exists. It will optimize the use of instructions and switch things when it needs to do that. Okay, so that's early '98. They went public, and then these are all links over on it. Oops, not there. There. So here it shows some of the different ARM Cortexes. Again, if we have the A series, it's again meant for something like a phone, something that has more application oriented is the way they call it. A is for application. R is kind of for real-time control, something that maybe you'd put into things that really needed to have a guaranteed date. So if you were using mission critical things like it was a controller for a heart monitor in a hospital or something like that. It was those kind of things. And then they found that Cortex M series was basically the things that we are after, like in the microcontroller end of things. One thing I'd like to point out in that, you see Up here we have nested vector interrupt controller. That you guys used interrupts this week, and that's the nested vector interrupt controller. When you just checked off that you want to have your A to Ds, it had that interrupt service procedure, put in your it.c file, and the nested vector interrupt controller gets that interrupt and then says where in the vector table you go, which is that ADC IRQ handler that was found in that startup file. And it says, hey, go to the ADC IRQ handler that's in your it.c file, and then it goes and services the interrupt. Okay, and it can handle things from UARTs and up to 240 different ones. Then over on the right-hand side of that Cortex-M, we have a debug and this trace macrocell unit, which is all about sending the data through to your debug channels. In fact, next week, we are going to use DMA, and then we're going to use an external program to hook in, and as your code is running, look at some of your variables. And it does it through that. And it just takes snapshots and sends that data out and lets us graph it and do all of that kind of thing. So that's where we're going with all of this, utilizing some of the debug features. That's kind of, oh yeah, I wanted to show you this too. Back in the 1985, this is 6,000 gates, ARM1, and so 7mm by 7mm, and so this is 0.07mm by 0.07mm, has 2,000 more gates, and is that size in comparison. So, 2010 from 1985, and it's saying, hey, in that tiny, little spot, we've got 2,000 more gates. We're 20 nanometer, and this was 3 micrometers. So the technology has really evolved. The smaller I can make it, the less voltage I use, the less power I use, hopefully the less heat that gets generated. And anytime you see it says here's a Cortex A9, which is 100 million gates. So, that's an A9 that's used in one of your latest phones. And the Mali 400 is a graphical processing unit to be able to do that. So that was kind of just interesting in seeing those. Okay, this is again one of your links here, and it's to date, ARM partners have shipped more than 160 billion ARM-based chips, and an average of more than 22 billion over the last 3 years, and it's just been growing and growing. It's kind of like the board that you are using with Wayne, it's an ARM. The Raspberry Pi, it's an ARM. If you're an Apple phone, it's an ARM. If you're an Android phone, it's an ARM. If you have a DVD player, GPS, it's an ARM. There are still lots of other things out. You might look at a heating controller, probably is a pick on board. If it's got Wi-Fi connected, if you go to Costco and you buy some wireless plugs, they'll actually be ESP 32s or 8266s, which you have both of, and we will look at later on in this course. Okay, and so record shipments, again, 160 billion. Nope, there we go. And this, I don't know if it's regulatory approved yet, but NVIDIA was to acquire ARM for 40 billion from SoftBank. Now, SoftBank's still maintaining about, there's share transfer agreements. It's not all cash and things like that. So SoftBank is going to still have an interest in ARM doing well, and whether or not it's been has the regulatory approval and stuff to be able to pass yet. But anyway, that'll be interesting. Now, one of the other things I wanted to look at here, one of the reasons you can't get cars and used cars are so hard to get right now and so expensive is they have problems with being able to get microprocessors. And this link says between 25 and 50 CPUs controlling car functions, often network, but sometimes operating independently. So things have really, you need microprocessors, and a lot of microprocessor manufacturing during the pandemic was people were sent home, people were quarantined, all the rest, and there's been a real supply chain backlog in just everything, even in shipping and all the rest. I saw on the news, and it was saying that places like Costco and Home Depot were getting their own ships or somehow acquiring their own ships and their own shipping containers to try and get around some of the supply chain issues. Anyway, so we're looking at 25 to 50. I wanted to then look at this here and just as far as this is one of there was the page of all the links, and then I have a couple other pictures. This is one of them there, and it's just the automotive semiconductor market. And I just wanted to go down and just show you kind of this little table. And it shows a difference between consumer electronics and automobile electronics. And it says, as far as the process technology, you're 28 to 7 nanometers in the ability to go and put things on silicone. Automobile electronics can be bigger, 180. Temperature range, you know, typical consumer electronics, they're 32 to 100 degrees Fahrenheit, whereas in automotive, it's minus 40 to 300 degrees. So you could have the car sitting out in the Phoenix sun, cooking itself, and it has to be able to survive that. It could be, you know, in the Arctic, and haven't been plugged in, and where, you know, if it's really cold, they'll warm the battery and things like that. But here, the chips have to be able to survive extreme conditions. Operating lifetime, they assume electronics for consumers is 3 to 5 years. In an automobile, they know that you're not buying a new car every 3 to 5 years. It's got to last 15 years at least before there's any issues. As far as tolerated failure rate, in consumer electronics, less than 1,000 parts per million. So 1,000 devices fail per million. If you're under that, you're saying, hey, we succeeded. In the automobile, you know, if a chip goes bad, then you have a whole car that's not working. They say 0 parts per billion. So the reliability, so it takes a long time for them to choose a chip, takes a lot of testing. And so when they have these parts issues, it's not like they can just go grab another part. They have to be vetted and tested and all of the rest. Long-term supply need, consumer electronics, no, you just use the next part that comes out, hopefully. And with automobile electronics, the manufacturer has to guarantee that that chip will still be around for 30 years. And so there's quite a difference in the demands for the automotive. Now, one of the things, you know, we've said that ARM is in everything, and that you know, and that's why we wanted everybody to be able to at least say, I've worked with ARM. You can fire up a development environment, and I'll show you some other development environments that are with it as well. And but there are some other things on the horizon coming. RISC-V, for instance, you might have seen or heard RISC-V. It's an open standard instruction set. It's a RISC as well, and it's under open source licenses. So one of the neat things about this, it came from the University of Berkeley in 2010, and there are chips that you can actually buy now, but they kind of like they designed this reduced instruction set computer, but they put it all open source. They have a whole consortium of people saying this was good, this wasn't good, and they finally came out with this standard, and then they put it out there. So the intellectual property is there, and you can go get it, and you can build your own RISC-V computer, and you don't owe anybody anything. That's part of the whole open source. Now, if you make changes and it improves it, you make that available for anybody else to then take your ideas and then do something else with it. So the whole thing, hopefully you benefited from everybody else's design, and you help other people benefit from your design. Now, RISC, is still not really there in the market really at all. But it does concern the ARM folks so much so that the lower end ARM products, the ARM M0, which you can go and buy, we're in the M4s, and you go down to the M0s, 32-bit, more inexpensive. I can probably buy one for under $1, kind of thing for some of the different 32-bit devices. But they have waived the IP licensing for any of the M0s because they're worried about this, right? And so these are getting in the next probably year, you're going to see some RISC-V units that can operate in a desktop environment and things like that even. Western Digital has on all their hard drives now, they've replaced the microcontroller with a RISC-V, which means they manufacture it. They don't pay anybody any licensing fees for all of that. So that's something. So if you hear RISC-V, it's RISC. It's along similar veins of what we have with our ARM series. There's going to be all sorts of different variants, just like we saw all the architectures for ARM scaling from desktops all the way down into microcontrollers, and no one pays any licensing fees. And some of the early RISCs were kind of expensive chips. You can get some, I could probably buy a RISC-V board to play around with in the maybe the around the F4, maybe a little less powerful on that series for probably 15, $20 now. They have some in the kind of more of the phone kind of category. They still want a few $100s for that kind of range right now, but it's early days. But I just want to show you, it's got ARM nervous there, and it's good. The competition's good because already you can put an ARM M0 in an FPGA and not pay anybody anything. So there are some soft processors gone into FPGAs that do that. Okay, so that's where we have some of our RISC-V stuff. One of the things I said about putting something in an FPGA, a few years ago, Wayne and I went down to Altera down in California, and we were they had a training session for putting CPUs into FPGAs. So you have a development environment, you write your C code, and then it's really kind of neat in that you have your soft CPU, and that it was you write some code, and then you have a function that does something, and then it's running too slow. So you can target the function and say, turn that into gates, and it puts the ones and zeros, and it's no longer code running on your soft processor. It's actually gate level board, and you get a dramatic increase in your function speed running. I gave up some of my silicone to put that part in, and it was really kind of neat. Some of the people that were there, we were talking to some, were from companies like Raytheon, for instance, and some engineers, and we're going, wow, that's interesting. They do the cruise missiles and do all of this kind of thing. Well, they have needs kind of like automotive industry, even more so in that they need to vet all the lines of code that was written, because if you do things that are fly-by-wire and something goes wrong with the code, bad things could happen. And so it cost them, it was thousands of dollars per line of code to have it vetted and checked. So they have a team going through and making sure somebody didn't screw up their code and something could happen and a cruise missile go where it shouldn't go, or something like that, or some fly-by-wire thing fall out of the sky. And so the problem that they were having was the code that they had put onto the CPU that they had been using was no longer made. And so they bought all of that they could from all the different distributors, but the company that sold them the microprocessor was no longer manufacturing it. So that meant when they go over to another chip, they had to do that whole vetting process all over again and make sure there were no issues with the new chip. So they were going to soft processors because you have, in Altera, for instance, you have an FPGA. If that FPGA ever disappears, it's just a bigger set of gates, and your IP configures just like it did on the other one on the new one. So they would have to do the vetting process to get it into the FPGA, but once they did, that could transfer across all of these different chips. So they were seeing this as a way to get around this end of life issue, kind of thing. So interesting with the FPGAs. You have the ability with the FPGAs that you use to put in a soft processor and write code and do the whole development environment. One of the things you can now do license free is the Cortex M0s, and they can be dropped into an FPGA and that whole thing. Going to kind of leave it there, I think, today. Next week, we're going to do DMA, so direct memory access. We're going to use another piece of silicone. We're going to do it to the same thermistor and die temperature, but this time we're going to tell that other piece of silicone, whenever the data comes, just go stick it in memory and just do it behind the scenes. And your code never looks at it after that other than to go to the memory location. So that's what we'll do on next week's lab. Thank you very much.